So today, we know that atoms make up all matter. Okay, and matter has to have both mass and volume to be considered matter. Okay, but way, way, way back, he had a pretty extreme idea, and Aristotle had pretty extreme ideas. And so his theory said that he thought all matter could be broken down. It was divisible. We can break it apart. Okay, he said until that basic unit was reached, everything could be broken down. Okay, we can put it in smaller and smaller and smaller pieces until the basic unit was reached. Okay, and he called this basic unit an atom. Does it sound similar to what we know today? Pretty similar, right? We can break down, a chunk of something until we reach those elemental atoms, right? Until we reach an atom of carbon and an atom of oxygen or whatever it is. But he called this most basic unit the atom, which he said was indivisible, was unbreakable, right? We know now that there's smaller parts even within the atom, but he said that essentially this is as small as it goes, okay? Today we know that the atom is the smallest part of an element that can retain all of its individual properties, right? So the atom is the smallest part of the element, but today we know it can be broken down a little bit further. This guy was not well followed. No one believed what he had to say. Because of this next guy. Okay, the next guy is Aristotle. Have we heard of him before? Right, he was really famous in philosophy, religion, all that kind of stuff, but he also made extreme contributions to science. And his thought process was that matter was a whole, so matter acted as a whole, you can't split it apart. And his thought process was pretty extreme, yet everyone believed him, right? He must have been a pretty persuasive guy because everyone believed what he had to say. He said that everything in the earth was made up of just 5 elements. And his definition of an element is much different than we know today of an element. Okay, and people followed his ideas and his thought process for over 2,000 years. That everything in the earth was made up of just 5 elements. Once we start hitting what we consider modern scientific times, which the 1790s, everyone is obviously considering really modern, okay? Once we hit those 1700s, people start getting a little bit more curious about science and what it means to give a chemical reaction a quantity. Okay, so when we say a quantitative nature or a quantitative assignment, that means we're putting numbers to our chemical reactions or to our experiments. Okay, quantity means numbers. So quantitative means we're starting to put numbers now to our chemical reactions. So that was their concern. In the 1790s, they already kind of knew at this point what a chemical reaction was, right? What has to happen in order for it to be considered a chemical reaction? Or what's a good indicator that a chemical reaction has taken place? It changes the identity. Good, right? We have some sort of big change that happens in order for it to be a chemical reaction. So a new substance is formed, or there's been some major change. So at this point, they knew what an element was, what a modern element was, and they knew what a chemical reaction was. So now their concern is, how do we put numbers to these chemical reactions? How can we start looking at the values that goes into these chemical reactions? So this led to what we today know as the law of conservation of mass. And we talked about this just a little bit prior. What does the law of conservation of mass tell us? Matter is neither created or destroyed. So mass is neither created or destroyed. You can keep it at that. You don't have to write out this full book definition, right? If you know that matter is not created or destroyed for conservation, that's great. This says during ordinary chemical reactions or physical changes, it only changes form. So matter, like we said, doesn't go away or come from nothing. It just changes its form. Okay. So during a physical change, let's think about a physical change of water from liquid to a gas. What's that called? If we go water from a liquid to a gas, what's it called? Evaporation or boiling, right? That's our boiling point. Doesn't the water eventually start to go away? Right? If you're boiling water on the stove, and you boil and boil and boil for a long time, doesn't the volume in the pot start going down? Is those water just disappearing? No, what's happening to it? Yeah, it's just turning to gas or water vapor, right? And then it eventually floats away. It will condense if it gets cool enough, but it's probably not going to condense back inside the pot, right? It might not be able to condense back there. So eventually it's going to float away and it'll condense again or whatever, but it's not necessarily leaving. It's still in the system. Okay? So this quantitative search or research that they were doing also led to something called the law of definite proportions. And this is much less common than the law of conservation of mass. We hear about that all the time. But the law of definite proportions tells us that a chemical compound, so once we consider something a compound, it contains the same elements in the same proportions, regardless of the size of the sample. Okay, so let me underline just a couple things here because that's a lot of words in our definition. Same elements in same proportions, regardless of the size of sample. So once a chemical compound has been established, right, it has a set name, it has set properties, and it doesn't change. Right? If we change one of the elements in a compound, it's no longer that compound. And oxygen. So can I have one oxygen and one hydrogen molecule and it be considered water? No, right? The formula for water is H2O. So that means unless it has two hydrogen and one oxygen, it can't be considered water, right? We can have H2O, we can have H3O plus, we can have OH minus, right? We can have lots of different combinations of hydrogen and oxygen, but it's not considered the water compound unless it's two hydrogens and one oxygen. So that law of definite proportions tells us that once a compound is set, there's no taking away elements, adding elements, otherwise it's no longer that compound. Okay? So it's a lot of words for what we would consider a pretty simplistic definition. Okay. So taking what we know about compounds, right, they can be combined multiple ways, but it gives us a new compound every time. They understood that hydrogen and oxygen don't only combine to form water, right? If they combine in a specific way, it forms water, but they can combine lots of different ways, okay? So carbon and oxygen, for example. Do we know any compounds that can exist between carbon and oxygen? Carbon monoxide. Good. And the formula for that is just CO. Right? Monoxide tells us there's one oxygen. What about another version of that? Carbon dioxide, CO2. Right? Those are two different compounds, but they're both formed from a ratio of carbon and oxygen. Okay? So two elements can combine to form multiple different compounds. Okay, so this is called the law of multiple proportions, right? We have definite proportions and multiple proportions. Okay, compounds are formed by whole atoms chemically combining in different ratios. Combining by whole atoms, that's important, right? H2O couldn't be H1/2, right? That's not how it works. It's not just the ratio of 2:1, hydrogen to oxygen. Even this won't work, H4O2, right? That behaves differently than water. Okay, so it's all about the ratio that forms the compound. So this doesn't work, right? We can't ever have half of an oxygen atom. So we have to always combine in whole number ratios. Okay, sorry, do we have what we need here? Back one more. Mm-hmm.
Oh, I was talking about what we just had.
This guy named John Dalton, a school teacher, much smarter than me, obviously, came up with what he considered to be an explanation for all of these different laws, right? The law of conservation of mass, multiple proportions, and definite proportions. He came up with what he considered an explanation for these laws. Okay, and so what I'm going to show you is I'm going to show you his definition, and then in red I'm going to give you the real, what we know today that's different. Okay, so we know a couple different things that are contrary to his law. Okay, so this is called Dalton's theory. Okay, he said matter is composed of atoms, and only whole numbers of atoms can combine to form compounds, right? We agree with that. We looked at that. Okay, and you can write this in extremely abbreviated form. Okay, I just want you to make sure you hear it. So he said matter is composed of atoms. We can only form compounds from whole number atoms, right? We just saw those laws tell us that. So his explanation is just kind of reaffirming that. Okay, so his theory is as follows. Okay, he was confirming those three laws that he understood what they were saying. Now he's explaining why those are the case. Okay, so this is called Dalton's atomic theory. He said all matter is composed of atoms. He said atoms of an element, I'm going to take that out. Atoms of an element are identical in size, mass, and other properties. And then the kind of counterpoint to that is atoms of different elements. They're different in size, mass, and properties. Okay, so what he is trying to say here is that every oxygen atom weighs the same, acts the same, looks the same. Okay? But oxygen and hydrogen atoms don't weigh the same, don't act the same, don't look the same. Okay, that's what his point right here is telling us. He says every oxygen atom looks the same, acts the same, weighs the same, but hydrogen and oxygen don't act the same, weigh the same, or look the same. Okay? However, there's a little caveat to that. Today, right, the red is what we know differently today. Today, we know that atoms of the same element can have different masses. So not every single oxygen atom weighs 16. Not every single hydrogen atom weighs 1. And we're going to dive into that a little bit later, maybe today, if not tomorrow. But today we know there's a difference there. Okay, so not every single oxygen atom weighs the same. What does an element have to have? What's the only thing an element has to have to identify itself? The number of protons, the correct number of protons, right? Anything else can be changed. It can have a charge, which means it has less than or more than the electrons it should have. It can have a larger mass or a smaller mass by taking away neutrons. But protons is the only identifiable thing that we can use to confirm an element's identity, the number of protons. Okay? A lot of other things can change. Protons cannot. Okay? So he said that atoms cannot be divided, created, or destroyed. Today, we know that we can create man-made elements. So that means we're creating these elements, creating these atoms. We can split atoms, and we know there's smaller parts to the atom. So he was a little bit off there. Okay? He said atoms cannot be subdivided, created, or destroyed. Today, we know we can make man-made elements. Okay, which doesn't necessarily mean we're making matter from nothing, but we're combining certain things to form an atom or an element. And then his last two things are pretty self-explanatory, so you can abbreviate those way down if you want. We already talked about those a little bit. Okay, so Dalton's theory, and then we had two little things that we know differently today. Okay, so on this next slide, the only thing that I want you to take away is the modern or today's definition of the atom. Okay, we probably already have it in our notes somewhere else, so if you don't want to write it down again, that's fine. But modern atomic theory, we know all matter is composed of elements, atoms of one element different from other elements, But today's definition is what I want you to have if you don't have it yet. Okay, the smallest particle of an element that retains chemical properties of that element. Okay, if you don't have it down or you don't know that off the top of your head, I want you to write that down. The other two parts of the atomic theory I think we know. Okay, so a proton, does it maintain any properties of an element? Does a proton act like oxygen? No, right? Protons make up atoms. Atoms then, with the right combination of things, will act like certain elements. So that's the important part there of that definition. Okay, so now we're going to walk through kind of all of these subatomic particles and their discovery, what they look like, what they do, what they act like, all these kind of things. Okay? So discovery of electrons. Anyone know off the top of their head who discovered electrons? Have you talked about that before? A guy named J.J. Thomson. Okay, he did an experiment with metal. And his metals experiment essentially told him that metals give off this negative charge. I don't know why yet, but he found out that these metals give off this negative charge. Okay, so he's trying to think about what these things should be called, right? Or what are these things? So he called these particles electrons. Particles that give off a negative charge are called electrons. Okay, so he named them electrons. And since he understood that they have to be in every single metal, he then was able to confer that every element has to have electrons of some sort. Okay, everyone has to give off this negative charge. Okay, so after much time and experimentation, he found out, maybe not even he, I don't know necessarily, but the mass of the electron was found to be 9.103 times 10 to the negative 31st kilograms. That's a small fraction of a kilogram, okay? And we'll see with comparison to a proton and a neutron, its mass is negligible. We ignore it. Right? We don't consider the mass of the electron when we're finding an element's atomic mass or its molar mass. Right? We don't count for electrons. We count protons plus neutrons. Right? We don't even care about the mass of the electrons because they're so small. Okay? So knowing now what we know, that there's some sort of negative charge going on in elements. There's something that's giving off a negative charge. But atoms are, for the most part, neutral, right? Most atoms are neutral, or all atoms are neutral. If something's giving off a negative charge, yet our element as a whole is neutral, what has to be happening? It's got to have some positive charge to counteract that negative, okay? So that's what he's saying, right? Since atoms are neutral to begin with, right? Neutral meaning no charge, and he knows there's a negative charge being given off, there's got to be something that's giving off a positive charge, okay? And we know that those are called protons. Okay, protons give off a positive charge. Okay? So that's how there was a conclusion as to these things called protons, right? And I'm giving you extremely simplistic pictures of these experiments done, right? Where you can dive a lot deeper into how these things were discovered. I'm giving you a pretty good overview, right? A broad overview. All right, so he knows got to be something to counteract the negative charge is a proton. Now he knows electrons weigh so little, there has to be something else contributing to the mass of an element. Can't just be the protons. So what's the other component that contributes to the mass of an element?
Neutrons.
The neutrons, okay? So protons counteract the negative charge with a positive charge. Neutrons don't give off any charge at all, but they add to the mass of an element. Okay, this should all be reviewed to you, and I'm sure it is. Okay. So his original vision of what the atom looked something like this. right? He thought there was a positive charge from these protons, and the negative charges just kind of counteracted each other. That was his original vision. Is this what we kind of think of today? Not so much, right? We're going to get to what we think it looks like today and how that was discovered. But that was his original thought process, right? There's some sort of positive charge distributed throughout the atom, and the negative charges are distributed all over, right? That was what his thought process was. So now let's move on to how we discovered the nucleus, okay? So a guy named Ernest Rutherford is a name that should sound pretty familiar to you in this scientific world. He has a specific model of the atom that we're going to look at. But Rutherford did this experiment called the gold foil experiment. And the book so pleasantly describes it as bombarded this gold foil with what were called alpha particles. Okay, and alpha particles are positively charged particles that are 4 times heavier than hydrogen. So positively charged elements that have a mass of 4 AMU, right? But the important part here that I want you to think about is that they're positively charged. Okay? So these particles, they're not neutral atoms, they're positively charged, and he's running them through this gold foil, right? He's pushing them through this gold foil. So his expectation was that these particles would pass right through the foil, right? Nothing getting in their way, nothing doing anything, because at this time they thought that atoms were one, big charge that was neutral, right? One positive counteracted by the negatives, right? So they thought they were neutral atoms. So if a positive runs into a neutral, nothing's going to happen, right? So this is what he was expecting to happen, right? Very little deflection. He thought if it hit an atom at all, right, it would be able to pass right by it or right through it even, okay? Because those negative charges aren't going to deflect to positive, right? What happens if a positive and a positive see each other? They would deflect, right? They would deflect. Just like with magnets, right? You put 2 wrong ends together, they're deflecting. If you put a wrong and a right end, right, a positive and a negative end, they're going to stick. That's what his expectation kind of was, that they would pass right through this gold foil, no problem. But that's essentially what happened. Most of them passed through, but some particles were redirected. As soon as they hit that gold foil, they bounced off. Okay, they hit and deflected. I doubt it. I bet he had some sort of sensor that told him where they were ending up, but you can't see individual atoms. So I don't know if he used a light source or something, but you wouldn't be able to see individual atoms going through there. Okay, so some of them passed right through and some of them were redirected. Okay, so his conclusion was that in an atom, there has to be some positively charged region of an atom that would cause this positive particle to deflect. Okay, so rather than the whole atom being neutral, his conclusion was that there's got to be some positively charged part of it that's making these positive particles deflect, right? Because if a positive would hit a positive, they should bounce off of each other. Okay, does that part make sense? So why did most of the particles pass right through? What does that mean? Yeah, William? Yeah, they passed through the electron cloud. They didn't ever hit a nucleus, right? The nucleus is where that positive charge is culminated in an atom. So he just assumed that some of those alpha particles were hitting the nucleus. Most of them were not, right? Those are the ones that could pass right through. They didn't hit a nucleus. Okay, so this is what he said. That dense region with a positive charge is going to be called the nucleus. Okay, and his model, his Rutherford model, he based off of this conclusion, that there's a dense region in the middle of an atom that holds a positive charge, and the electrons orbit the outside just like a planet. Okay, so Rutherford's model is also called the planetary model. All right, and I'm going to show you another picture of his experiment and of his model here in just a second, so I'll give you a second to draw that out. But he was the one that discovered the nucleus based on this gold foil experiment, right? He pushed these positive particles through. The ones that were deflected, he said there's got to be a positive charge in there somewhere that's causing these to deflect. So he said most of the volume of an atom is empty space, right, where the electrons are not located because they're moving so quickly around the nucleus. That's how those alpha particles are able to go through. And his is called the planetary. So here's kind of a picture of what this looked like. Right, the alpha particles were coming out of a radioactive source. They went into the gold foil. You see 3 here were deflected. The rest of them flowed right through. Okay, so that's how he kind of saw which ones were deflected and which were not. Okay, so that means his new model of the atom has to look something like this, right? There's a positive charge in the middle of it. Electrons are orbiting or floating around the outside of that atom. Okay, so his model looks something like this. If you want to draw that out, you can. Right, this is what the planetary model or the Rutherford model of the atom looks like. Center that contains a positive charge and electrons that orbit the nucleus like planets. Okay, that's more on track with what we know today. Closer than Thomson was at least. So today we know the nucleus contains 2 particles. What are they? Protons and neutrons. Okay, protons give off a positive charge. They have a mass of 1. And neutrons give off no charge. They have a mass of 1. If this is review for you, you don't have to write it down. It's okay. Okay, I get it that you've seen this before. Okay, so we know the nucleus contains protons and neutrons, both of which have a mass of 1 AMU. What does AMU stand for? Do you remember? Atomic mass unit. Good, very good. Okay, and neutrons have no charge, also mass of 1 AMU. They're held together by what we consider nuclear forces. Okay, nuclear because they're located within the nucleus. So protons and neutrons are hard to get apart. Right, it's hard to break that apart. So they're called nuclear forces because they're held within the nucleus. Okay. So how do elements differ from one another? What's the one identifiable quality? We've already talked about it today. Number of protons. Okay, number of protons is the one identifiable quality that differs elements from one another. Okay, that's called the atomic number. So if you don't have your periodic table out, why don't you go ahead and grab that out now so we can look at a couple. Okay, this number never, ever, 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 ever will change. Proton numbers never change. Anything else in an element can change. The mass can change. The number of electrons can change. Name, number of protons, or atomic number will never change. Okay? Something else to think about is that in a neutral atom, what's the charge of a neutral atom? 0, right? So in a neutral atom, the number of protons has to equal the number of electrons. Okay, so if I ask you how many electrons does oxygen have, a neutral oxygen atom, how many electrons does a neutral oxygen atom have? What are you going to tell me? 8, right? Not 16. 16 is the mass. 8, it has 8 electrons, 8 protons, 8 electrons. Okay, so in a neutral atom, protons equals electrons, right? You might want to write that part down. Okay, atoms always have the same number of protons, but they can have different numbers of neutrons. That's where we talked about the mass can change. They can have different numbers of neutrons. Okay, and these are called isotopes. This is a vocab word that you should know or get familiar with if you don't know it already. Okay, have we heard the term isotopes before? Good. Okay, isotopes are same element, different atomic masses, which means different numbers of neutrons. Okay, because the number of protons won't change. Right? If I add a proton to oxygen, do I still have oxygen? What do I have? If I add a proton to oxygen, what do I have now? Fluorine, right? I don't have oxygen anymore. So anything with 9 protons is fluorine. But I can have oxygen that has a mass of 17 or 14 or 18, right? Those are just changing the number of neutrons. Okay? So isotopes, the definition of isotopes are atoms of the same element with different masses. Sometimes isotopes even have different names. And I'll show you an example here with hydrogen, and it's isotopes. Right, this original hydrogen up here on the left, it's just called hydrogen, right? It's got one proton, one electron, no neutrons at all. The next one's called deuterium, okay, which is H2, right? It's not really H2 because it doesn't have two hydrogen atoms. It's got one proton, one electron, one neutron, so it's got an atomic mass of 2. Then tritium has an atomic mass of 3. Still only has one proton, but it's got 2 neutrons. Okay, so all of these are versions of hydrogen, but they even have their own name.
So what would be things that would cause the mass?
Again, we're going to look at isotopes or elements, isotopes of elements that have really close to whole numbers when we calculate that. I would make you can't have a fourth of a neutron, right? I'll show you next class how we calculate the average atomic mass. But if I wanted the number of neutrons in a neutral oxygen atom, what would you tell me? Right, assuming its atomic mass is 16, we would have 8 protons and 8 neutrons. Okay, so that's how we find that. So if we want number of neutrons, we take atomic mass minus the atomic number. Okay, last thing we're going to talk about today is what if our electrons and our protons have different values? What if we have different numbers of electrons than protons? Now it becomes a non-neutral atom called an ion. This might be we're getting into new territory here. Yes or no? No? Okay, good. Ions are charged particles. Oops. Okay, so an ion is any atom or any element that has a charge to it. That's it. There's going to be specific names for positive and negative. We'll get to those probably next class. But if we have more electrons than protons, does that mean we have a positive charge or a negative charge? A negative charge. Good. Okay, if we have less electrons than protons, what does that mean we have? A positive charge. Okay? Very good. Okay, so how would I describe lithium with one less electron? How would we write that? Good, we'd write it as lithium plus, right? And if it's a 1, if the charge is ever 1, minus or plus, you can leave the 1 off. Okay, just a little tidbit. If you have oxygen with 2 extra electrons, how would we write that? Yeah, good, O minus 2. Our charges are always written as superscripts, right? I think that's what they're called, like an exponent, right? Up and to the right, where we write our charges at.